if you maybe could stop a little bit earlier so that we can have questions.
Yeah.
In any case, our session lasts until 1:30 UTC, and the next session will be at 2. So if we are a little late with the end of the session, there will be no problem, I guess.
Okay. Thank you.
Recording in progress.
All right, so perfectly in time, we can start with session 2 of Laser Physics 23. I welcome everybody. I'm very pleased that we were able to find in this seminar many very interesting speakers with many interesting talks. And I'm also delighted that we have so many participants in session 2. It's actually about 90 persons who have registered, and many of them are now in the session. I have asked the speakers to maybe not use 100% of their time so that we can allow for questions at the end, and I will maybe give them a note when they are obviously not stopping with their talk in time. Also, you can write questions into the chat, and I would ask these questions then in the end. All right, so I think we can start. I'm very pleased to welcome Jérémy Caillat from Sorbonne Université in Paris, France. He will tell us about 2-photon transition delay inferred from interferences with 1-photon reference transitions. And I'm glad that you are here and welcome you and looking forward to your talk.
Thank you very much, Reinhard, and thanks to the organizers for letting me the opportunity to present these results that were obtained in collaboration between the group of experimentalists of Pascal Salière at CEA Saclay and 2 theoreticians, including myself from Sorbonne University. So the context of this work is the study of photoemission in the time domain that was made possible over the last 15 years, more or less, with the tools of attosecond metrology. And the dynamics of photoemission were first interpreted in terms of scattering dynamics, scattering of the photoelectron over the ion potential as it escapes from the atom of molecule. And they were characterized either using scattering delays or in terms of more complex dynamics in case of, for example, autoionizing dynamics. And today I will not talk about these scattering dynamics, but rather about the dynamics that's taking place before scattering, during the transition from the initial state to the continuum. And such dynamics occur as soon as there is more than 1 photon involved in the process. And I will consider cases where those dynamics can be interpreted in terms of, or characterized in terms of delays. So I will first give definition of transition delay. So let's consider a 2-photon process leading to ionization. And it has a probability amplitude associated with it. It's a complex amplitude. So it has a phase, and from that phase, we can define a group delay that we will call transition delay. So before presenting how such delays can be measured, I will show some results of numerical simulations which give some insight on the interpretation of these delays, how they have to be understood. So we considered a model atom in our simulation, which has a resonance, a shape resonance in the continuum with a 1.7 femtosecond lifetime. And we simulated 2 photon ionization with 1 photon which is nearly resonant with that resonance. And from that model atom, we could compute the transition phase using second order perturbation theory and the transition delay. And what we considered always a final, a given final energy, and we just tuned the photon frequencies to scan the resonance. So this is what we obtain. As a function of the large photon frequency, these are the delays, which are actually, this is not attosecond, it's femtoseconds. I'm sorry about that. And the delays increase up to 1 femtosecond when the first photon is resonant, and then it goes down again. Now, we want to know how, to which extent it's representative of the actual dynamics. So we simulated the same process with the time-dependent Schrödinger equation and computed the outgoing electron flux at some distance from the atom. And this is what we obtained. This is the flux as a function of time computed here at 4,000 atomic units. And from that flux, we can compute an average time of flight. Okay, it's just the average time under this curve. So this time of flight is not so meaningful as such because it depends on the detection distance, naturally. So we want to compare. So since we want to access the dynamics which is related to the transition only before scattering, we want to compare it to a transition that would be instantaneous and ending up in the same final state. So we simulated that reference transition, which is a 1 photon transition starting here from the first excited state. 1 photon transition means that it's instantaneous, and it's the same final state. That means when we compare both of them, only the transition will differ. And so we obtain these time of flight in green, and we these flux in green, and we can compute a reference time of flight from it, and infer an effective delay as the difference between the time of flight of our wave packet of interest and the reference one. And if we plot it on the same figure, we see that they perfectly match. So this is some numerical experiments to show that this transition phase transition delay does carry information on the transition only, on the dynamics of the transition only. We did the same simulation on different model atoms with larger lifetimes, for example. It still works, and it also works when the transition goes through a smooth continuum. So, as I said, here you should read femtosecond, but here it's actually attoseconds. So when you go through a smooth continuum, the transition delay is very small, a few tenths of attoseconds. And the interpretation of the transition delay, the time domain interpretation of the transition delay still holds. So what we conclude from those simulations is that the transition delay is a signature of the electron wave packet temporal shaping by the 2 photon transition. It does depend on the pulse frequencies for fixed final energy. It's gated by the pulse durations. The transition need the pulses to take place, of course. And when one of the pulses is near resonance, then the delay can be interpreted as an effective transition duration. It's the time that the system spends in the intermediate resonance before completing the transition. So, what about measurements? So far, such delays have been measured using so-called rabbit schemes, mostly. I will not give a presentation on a rabbit now, just to give what's important for the present talk, is that in that case, the 2 photon transition we are interested in is probed by another 2 photon transition. And with an interferometric scheme, you get access to the phase difference between the two transitions, that phase difference. And it was applied to investigate dynamics, ionization dynamics in nitrogen through autoionizing states and in helium through bond states just below the threshold. With such schemes, you have to accept that you have access only to relative dynamics between the two transitions, the probed one and the probe one, unless you can calibrate your scheme with the reference amplitude. If you have some knowledge about your reference amplitude, then you can calibrate. So now what I'm going to present, the new scheme that I'm going to present is a scheme where we use an ideal reference transition which has no transition phase to have direct access to that one. So before presenting the scheme, I will show you the case on which it was applied. So it was applied to 2-photon ionization in helium through the 1s3p state. And for that, we've been using the 15th harmonic of an infrared laser and the infrared itself to induce the 2-photon transition. We reach the continuum near threshold. And with that, we create an electron wave packet, which is quite broad. The experimentalists use quite broad pulses. And once you have created this wave packet, if you wait for a given delay tau, the wave packet will accumulate an extra phase, which is just the spectral phase here, given by the time-dependent Schrödinger equation. But that's not only this wave packet that we are interested in, because the pump transition also created some population in the resonance state, and it also propagates during the same time with another phase which depends now on the resonance energy. And now the idea is to probe this wave packet with that reference state by inducing another 1-photon infrared transition. So we send an infrared again to transfer this state to the wave packet of interest. Now the phase difference between the two wave packets that will interfere is given by the phase difference of the spectral terms here that are copied here. They are oscillating with a frequency which is nearly the infrared frequency, because it's the energy difference here. And you have the transition phase that you are interested in. So in that scheme, you have an instantaneous reference. It's a 1-photon transition. You reach exactly the same final state. So all that concerns the scattering is removed from the measurement. And when you scan the delay, you get oscillation at the laser frequency, which give direct access to the transition phase of interest. So this is the experimental setup that I will present you as a theoretician. I will try to do my best. So the idea is to send a strong infrared laser to a gas cell containing argon to generate high harmonics. And then you let the harmonics propagate, and you keep a small fraction of the infrared together with it, and you send this combination of harmonics and XUV harmonics and infrared to the helium gas that you want to ionize in a velocity map imager, and you get such nice pictures of photoelectron momentum distribution resulting from that 2-photon infrared plus XUV pulse ionization. That's the pump arm. And now the probe arm is obtained by diverting a small fraction again of the infrared before generation, going through a translation stage, which allows tuning the delay between the pump and the probe, and then they recombine before being sent to the gas. And then you get interferences which are visible on the photoelectron momentum distributions. You see now some oscillations. And in that case, our experimentalist colleagues did their best to tune the infrared power to get similar infrared intensity in the probe and in the pump arm to maximize the fringe contrast. So these are the results. This here shows, this will be a movie which shows how the VMI pattern evolves when the delay is varied. And this is the angle integrated spectrogram as a function of the delay. So in the spectrogram, you see clear interference fringes which are curves of constant pump probe dephasing. So I will just show the movie if I have access to it. No, I have to forget about the pointer. Yes. Okay, so what you see at the beginning are very strong beatings which do not depend, the phase of which do not depend on the energy. The whole picture is beating in phase. And this corresponds to the beginning of the process. This is where the pump and the probe infrared overlap. So you have strong optical infrared interferences at the laser frequency, which do not depend on the final energy. And we are not interested in that part. We want to go further. And when you reach around 60 femtoseconds, the two pulses do not overlap anymore. And we enter a different regime. I will go a little bit further. And you see clearly that the phase of the oscillations depend on the energy. You have some kind of drift here, spectral drift along the time. And this is that part that we're interested in. This is further in the, get the pointer again, further in the delay scan. And here, the phase, the dephasing between the pump and the probe is given by the phase difference that I was mentioning, the spectral phase difference, natural spectral phase difference between the pump and the probe pulses, and the transition delay for the wave packet of interest. So now let's have a look at the data. We will analyze them in that region where the infrared do not overlap anymore. And performing a Fourier transform, we get this feature here. This is the photoelectron energy here and the Fourier frequency there. And you see that we have a beating frequency here, which is close as expected to the photon frequency. Just to make sure that we are properly analyzing this data, we plotted the central frequency of this pattern as a function of the photoelectron energy. So the beating frequency against the photoelectron energy, that is the curve here. And we see that is indeed linear in energy with a slope of nearly 1. And this is what we were expecting, the slope of nearly 1 because of this. This is from the experiment, and just to be even more confident with those results, we did some simulations and obtained very similar outputs. So next stage is to take this pattern, the Fourier transform, and look at the phase, because this is what we are interested in. So this is the phase of the beating against the photoelectron energy again within the support of the photoelectron wave packet. And this phase, if you remember what I mentioned before, I write it again here. It's it contains two terms. The first term is the spectral, natural spectral evolution of the phase, which can be plotted here. And what we are interested in is just the difference between the two. And I plot it here. This is the difference, and this is minus the transition phase which created our wave packet. Now that we have the phase, we can take the derivative. We get a slope of almost 20 femtoseconds, which is the transition delay for this specific case. So just to summarize the interpretation of this delay, we create one wave packet with an infrared and XUV pulse, we probe it with an infrared pulse after delay tau, and we find a transition delay, which tells us how long does the wave packet leave the atom after the infrared and X-UV pulse were sent. So the time in between is just the time that the system spent in the resonance. We repeated the same measurements. I say we, but my experimentalist colleagues repeated the same measurements with other resonances in helium by blue shifting the high harmonic generation process to reach the resonance 4, 5, 6, still with harmonic 15. And what they found is that they obtain a transition delay which is almost around 20 femtoseconds. It's here for all the resonances, because all those resonances have infinite lifetimes, infinite compared to the time scale we are dealing with. And what governs the delay here is mostly the pulse durations. And it's the same pulse durations for all of them. Which brings me to the conclusions. So I have presented here a new interferometric scheme to probe resonant 2-photon X-UV plus infrared ionization dynamics using an ideal 1-photon reference transition, which gives access to the transition phase and corresponding delay with no necessity for calibration with the reference. From the technical aspects, scanning the delay well beyond the overlap allows an accurate time domain analysis of the measurements. And balancing the pub and probe infrared intensities provides a highly contrasted fringe pattern. In terms of physics, of interpretations, the delay is measured for several resonances in helium, evidenced similar dynamics, around 20 femtosecond delays, which are governed by the pump pulse profiles, and no angular dependency on the photonation ejection direction were observed, which confirms that the same final propensity rules apply for the pump and the probe. That means that we reach the same final state in the two stages. So with that, I thank you for your attention.
Yeah, thank you very much for this very nice presentation and the interesting results you presented. Also, thank you for staying in time. We have time for a question or more. I would like to start with a question. So did I understand right that this delay that you measured is, so to say, the time, how long the system stays in the resonance?
Yeah, in that case, it can be interpreted as such. In the resonant case, it can be interpreted as such. It's the interpretation of group delays in general.
Yeah, and why does it stay in this resonance for that time? Is it understood, or did I just miss it?
Yeah, I guess so. If there were no infrared, only the X-UV pulse that populates the resonance, then we would have a lifetime of maybe on the nanosecond time scale, which is infinite for us, okay, or for the time scale we are dealing with. So it could stay there for nearly forever, and only the presence of the infrared takes the system out of this state. And how long the system will stay in that intermediate resonance is governed by the duration of the pulse, more or less. Okay. It's an interplay with both of them. It's like an effective lifetime for the resonance in that context.
Okay. Yeah, thank you. Got it.
Okay.
Are there other questions? Barry Walker, you raised your hand.
Yeah. So is this time that it spends is it intensity dependent, or since it's just a 1-photon transition, there's no intensity dependence for the lifetime up there?
Yeah. If you change the intensity, if you stay in the perturbative regime, then it shouldn't affect the time it spends there. But as soon as you leave the perturbative regime, if you induce significantly more infrared absorption, or if you stark shift your system, the transition will be different, so the dynamics will be different.
Okay, thank you.
So the delay that we got, we can reproduce it with second order perturbation theory very accurately, as long as we stay at the second order in the second order regime. If not, then we have to go to higher orders for the interpretation, but the principle would be the same. What's important is that the probe is perturbative. It should be one photon.
All right. I don't see any other questions, so let's thank Jeremy once again for the nice talk and answering our questions. And we proceed to the next talk given by Markus Osiander.
I will give you
on extreme ultraviolet meta-optics.
Did I stop sharing my screen?
Yes, yes. Okay, Markus should be able to share. Yeah, he does.
Okay, so I switch off my mic. Bye. Thank you.
Hi, everyone. And yeah, thank you for the nice talk. Having struggled with delays for some while, it's always nice to hear what's coming out of it and what people are doing new things in the field. It's cool. I switched fields from my delay time, and I went on to meta-optics. And today I want to talk about how we do extreme ultraviolet meta-optics. So that's where the attosecond perspective is coming back. And this is work that I started working on at Harvard in Federico Capasso's group. And then the experiments for this work were mainly done by Martin Schulze in TU Graz. And this is also the trajectory that I recently took from Harvard to TU Graz to start a group, or a small group. There's two parts to this talk. The first is extreme ultraviolet, and the second is meta-optics. And very briefly, why am I interested in this combination? So the extreme ultraviolet allows us to beat fundamental resolution limits. The first one is the spatial resolution limit, which is quite famous, given by the Abbe limit. And it tells us we can distinguish two features if they're spaced by more than the wavelength over 2 times the numerical aperture. And the numerical aperture is usually limited to 1, or if you have an immersion, maybe a bit more than 1, but you cannot scale it too much more, which means the features we can resolve are usually given by half the wavelength. And this means that achieving 350 nanometers spatial resolution at a wavelength of 500 nanometers means we need a numerical aperture of 0.7, which either requires a very large optic or a very short focal length. And both is bad for aberrations and for ease of working. If we can do the same experiment using a wavelength of 50 nanometers and want to achieve roughly the same resolution, we only need a numerical aperture of 0.07, which means either we can use a much smaller optic or go much further away, and all the spherical aberrations suddenly become feasible. The second limit is the EUV allows us to beat. This is the time resolution limit, usually given by the Fourier limit, which tells us that the product of the duration of a pulse and the spectral bandwidth, it must be larger than a constant. And for a Gaussian pulse, that's 0.44. I think that's the most used number. Now, this means if we want to achieve a time resolution of 1 femtosecond in the visible, we need 440 terahertz of bandwidth, which is 1.8 eV. And this means we need to cover the entire visible range in order to achieve 1 femtosecond, which again is very bad for aberrations, and it's even worse for dispersion. However, the Fourier limit doesn't know about the carrier wavelength, and this is really nice, because now if I can change my carrier wavelengths from 500 nanometers to 50 nanometers, the relative bandwidth I need is only 10%. It's the same absolute, but only 10% of the relative bandwidth, which means dispersion management gets much easier, and also chromatic aberrations gets much less. So why is not everybody working in the UV? And I think this is a thing that's pretty commonly known in attoseconds, is that there's no optics. There are Fresnel plates, which can make small foci, but they also create side lobes, and they don't achieve very high efficiencies. And everything else is essentially reflective. And in order to make a reflective optic in the EUV, we need to be very gracing to be efficient, which doesn't allow us to have any short focal length, and it makes aberrations really bad again. And I think a really nice work that was done about EUV, but it also tells us how desperate for optics we are, is this work from Berlin, where they used a helium plume in order to manipulate extreme ultraviolet radiation. Obviously, this works, but it's really hard to work with a helium plume on an everyday basis. And at this point, we were looking at what are actually other spectral regimes doing, and what are other technologies that can help us. And if you look at a lens, what makes a lens, it's usually the bulbous shape that's connected very closely to the function of a lens, but that's not actually true, because you can cut out cubes of glass from this lens and end up with this sawtooth shape, and it will still be working, it will still be focusing. And as you proceed to cut out more cubes, you end up at this very flat optic that just has this tiny sawtooth shape left. And at some point you end up realizing that it's the phase profile that makes this lens, not really the shape. And the phase profile of a lens is rather simple. It can be written down as a function of the radial distance, a function of the wavelength, and the focal length we want to achieve. And then what people in the visible are like perfecting now in the for the last decade, I would say, is that they make these meta optics, which now achieve the same phase shift, but not using this tiny sawtooth pattern, but they use nanofins. And these nanofins introduce in each position of the lens a tailored phase shift that then reproduces the phase shift of a normal lens and achieves focusing. But obviously, now that you use these nanofins, you can also make any other profile, not only lenses. And one example that this can be very useful is shown here. It's some work that I did with Christina Spegele, is you can superimpose many of these phase profiles and then achieve optics that can do multifunctions in a single optic. For example, in this case, we made an optic that creates an orbital angular momentum beam, a Bessel beam that doesn't diffract, and then a Gaussian beam in a single pass. And on the right here, you can see a picture of the optic and how these phase profiles are superimposed in a certain way to realize this. This is especially cool if you're doing laser feedback, or because you can send in a fundamental mode back to stabilize your laser emission, and at the same time shape the output beam, for example, like a hologram. In this case, it was the crest of the university I worked for. But it also has really interesting applications to ultra-fast physics. This is a work that was also done between the group at Harvard and Martin Schulz's group in Graz. Here we thought if we could design the dispersion of such a nanopillar coating in a way that it helps us with our ultra-short pulses. And the idea was that a piece of glass usually is annoying because it stretches a very short pulse. By delaying the blue components more than the red components. But if you placed a coating that's very specifically designed to have a resonance on top of this glob of glass, we could maybe make the resonance in a way that it delays the red components more than the blue, and then that the coating and the wafer together act like a compressor for these ultra-short laser pulses by putting all the colors into a single pulse again. Or you could think of putting this very, very thin coating on top of a thick optic like a lens, and then make the lens essentially ultra-fast pulse ready by compensating for its dispersion. Now we made such a sample. You can see it's these very thin pillars of silicon, and they work at 800 nanometer wavelength. and then we measured frogs. And we can show that the 41 femtosecond pulses that we sent in that were pre-stretched using glass were even more stretched if we just put in our substrate, so just the glass, to 49 femtoseconds. Then if we put in the glass with the compressor on top, it compensates for both the substrate and even another 5 femtoseconds of pre-stretched glass. So the 600 nanometer thick silicon coating can compensate for up to 1 millimeter of glass, which we think is really cool. And these are the spectral domain measurements. You can see that the white light interferometry really coincides well with what we did using our frog here. And then this is another work that I thought was really neat in ultra-fast physics, is the Amit Agrawal group, because they combined the spatial shaping, the polarization shaping, and the time shaping in a single experiment. And they could make these metasurface pulse synthesizers that have time-dependent polarization or time-dependent orbital angular momentum along the pulses. So I think in the visible, it's pretty clear that metasurfaces are really cool, but they all rely on introducing phase shifts. And this is either a propagation phase. Here on the left, I'm showing you a silicon coating, and you have less material, which means less phase shift. And here you have more material, that means more material, more phase shift. Or on a geometric phase, which is depending on the angle of these pillars. You see all the pillars are the same shape, but they're oriented in a different way, and they act as half-wave plates. And essentially their angle determines how much phase shift they introduce. But both techniques, again, rely on having high index materials, because the light has to be able to know if there's a pillar or there's vacuum or air around. So, and this leads to a problem in the extreme ultraviolet, because the refractive indices that we're used to, they're usually in the visible. And this means they're determined by the resonances that are electronic and in the ultraviolet region. This means that the visible resonances usually, visible light usually oscillates slower than the resonances, and this leads to no absorption, the red line, and a refractive index larger than 1 that we can use. However, if we go to the extreme UV now, where I just said I want to make optics for, the problem is that our light oscillates faster than the resonance. And this means that usually we have some absorption, but even worse is the refractive indices are always smaller than 1. And this is exactly what we don't want for our metasurfaces. Now, one good thing is that there is this TART rule, which means we have a off resonance, a window of transmission, then we have a window of absorption, a window of reflection, but then we have another window of transmission. So technically, at least light would go through our optics on this side, but still no refractive indices larger than 1. And I think this is where the step of this work really happened, is that we realized that we don't really need refractive index larger than 1, we need refractive index contrast. And now if we only have refractive indices that are smaller than 1, we can still make metasurfaces. We just have to flip our design paradigm by treating the vacuum as high index material, which usually you won't. But then if I make a hole of vacuum into my n smaller than 1 material, it's essentially like a pillar in the visible. So these are the exact equivalent now. And the nice thing of holes is that holes don't need a substrate, which lets us cut down on absorption by just removing the substrate. And then ending up with metasurfaces that have high index pillars of vacuum in a freestanding membrane. This is a simulation that shows that this should work. On the left, it's the refractive index of silicon, which at 25 electron volts photon energy, or 50 nanometers wavelength, is significantly smaller than 1. It's roughly 0.75. And in red, it's the transmission, which is 40% in this region. So pretty significant for EUV. And then we did a periodic unit cell, which is 120 nanometers by 120 nanometers and a 220 nanometer thick membrane. And we look at what happens to the light that's incident. And then we realized that this design method is actually nicer than we initially anticipated, because the high index vacuum region really sucks the intensity into it, like a silica fiber would suck intensity in the fiber core, which further increases our transmission through the metasurface, because now all the light propagates in the vacuum that has no absorption. And we were pretty happy about seeing this, and then started varying the diameter of the holes in order to create a diameter-dependent transmission phase, which we can then use to model our optics. And we realized that if we change our diameter from 20 to 80 nanometers, we can achieve up to 1.5 pi phase shift, which is shown in blue here, usually at transmissions between 0.4 and 0.6. However, because our unit cell size, and this was a fabrication choice, it's not the fundamental limit, but we wanted something we can make, is a bit larger than our wavelength, we get a bit of grading diffraction for holes that introduce a pi phase shift, which decreases efficiency currently. This is not fundamental. And then we can go back to our lens phase profile now, having this library of different phase shifts introduced by holes. And at each position R in our lens, we calculate the phase we need to focus a 50 nanometer ray of light. And then we match the phase to a hole diameter. And then we replace each phase by the hole diameter to get this map. And you see there's a pretty close correspondence. And then if we fab such a sample, it should be focusing. And the way it works is really, we have an incident plane wave, and then we introduce this a bit complicated phase pattern, and then the light knows that it has to collapse into a nice focus. In order to show that this works, we made samples, and the samples were mainly made by Marina and Daniel here, who used silicon on insulator wafers, which have this nice isolated 220 nanometer silicon membrane. And then we put electron beam lithography resist on top of these wafers. We define our structures using electron beam lithography, develop, then we etch the structure into a silicon dioxide hard mask, which we need for fabrication quality. And then we etch through the silicon. Once we have this entire metal surface essentially sitting on our wafer, we etch away the wafer in order to have a freestanding membrane. And then the result is shown here. So one Fresnel plate, you see that the holes get smaller from the inside to the outside of our wafer, and they correspond very well to our design, which is shown in red. And the entire meta lens is 1 millimeter in diameter, and the unit cell size is really 120 nanometers. So we have over 1 million of these cells across the meta surface. One nice picture I think we took while making this is one of a failed sample. So on the left, you see a sample that worked in fabricating, and it has these very dense holes all over the place. But one sample that failed is shown here, and you see only a third of the meta lens in diameter, but you see that you cannot even perceive the thickness of this. So this is really unbelievably thin compared to the diameter, which allows us to transmit extreme UV and make this lens work. Now, in order to show that this really is a viable way to manipulate EUV, I took the sample to Theo Graz, and Hannah Hampel, who's a PhD student in Martin Schulz's group, sent some harmonics into the sample. So we have near-infrared radiation, which we focus into an argon gas target to create high harmonics ranging from 1 to 40 eV. And then we have an aluminum foil to get rid of the driving radiation, and we send all the EUV onto our metasurface. And the metasurface interacts with all the EUV, and in order to look at the radiation at the design wavelength of 50 nanometers, we have an imaging grading after the focus, that splits apart the harmonic orders. And we're just looking at the 21st harmonic order in this case. The imaging grating has, due to the lack of optics, much smaller numerical aperture than our metasurface. That means we cannot look at the focus we create, but we have to also do a knife edge scan in order to see how small of a waist we actually achieve. And then the data looks roughly like this. The incoming beam in the plane of the metasurface is just a round extreme UV beam with a waist of roughly 0.5 millimeter. And then as we put our metasurface in, we can see that this really collapses into a focusing spot. And then we can get rid of the background by inserting the knife and taking a picture with the knife inserted and with the knife retracted and subtracting the two. And we see that this spot really corresponds to the light that's focused by the metasurface, but not to the size that the metasurface makes. In order to see how small of a focus we make, we scan the knife edge along the propagation direction and then into the beam at each spot, and we record how much intensity is transmitted. And at first you see that the light is disappearing slowly, and then as we approach the focus, it disappears faster, and then after the focus, it disappears slower again. So it's a clear indication of a focus. And if we really concentrate on the focal area, we achieve wastes down to 700 nanometers for a numerical aperture of 0.05. So really, this is unthinkable of in the visible, but in the EUV, we can achieve submicron resolution at essentially very small numerical apertures. And this is a summary of all the scans we took, and you see it really collapses nicely into a waist and then gets larger again. So this is a normal focus just created by a very weird optic. The question is, how good can this get? And currently we can make optics up to a numerical aperture of 0.2, which is much larger than I demonstrated just now. And in order to see how good this is, we compare it here to a Fresnel zone plate. You can see the zone plate makes nice small foci, but they always have these side lobes around them, which are intrinsic to Fresnel plates. The metal surface makes the nice, really the same nice small focus, but it has no side lobes here. It has just these grading orders that will never reach the detector and therefore not be detrimental to imaging quality. And if we cut through the focus, you can see really the beam quality is about a factor of 10 nicer than what we could achieve with a zone plate if we use a metasurface. And with this first proof of principle done, I think we're pretty happy to now look into applications, and we want to now make more complicated phase profiles. So as this hologram I showed you in the visible, we think we can bring this to the EUV, make EUV holograms. We want to build an attosecond microscope. Obviously, we can also make orbital angular momentum beams because we can just make the phase plates now in the extreme UV. We want to explore if we can use this in lithography, and we want to also explore if we can make those polarization-dependent optics. And with that, I'm done. So as I said, I'm currently working in Graz. I'm very happy to acknowledge some European Union funding doing this, and a START grant by the Austrian Science Fund, and all the colleagues, especially Hannah working with Martin and Marina working with Federico, that have made this possible. Thank you.
All right, thank you very much, Markus, for this very nice talk. Was really cool results. I liked them very much. Maybe I also start with the first question. So you have shown the transmittivity, which brings me to the question: how much radiation do they stand?
So I think in the EUV is always we couldn't break them, but also we have a high harmonic source, so it didn't see so much radiation, right? I do think that if you put them in like an 8-watt FEL beam, they will melt, but they should stand a decent amount. I know that the silicon nanopillars, which are much worse in conducting heat away from the sample, they easily stood rainbow oscillators, so like 300 milliwatts, and they are also absorbing. So they should survive pretty long, but like not 8 watts, yeah.
So what was the wavelength you were using with your harmonic generation source?
We used 50 nanometers now.
All right.
It's a bit of a trade-off. The technology works all through the EUV, but we have to be able to make the samples currently. And this is challenging still. Making a 20 nanometer hole is not easy. Yeah. So we think we can make them also work at smaller wavelength, but we have to scale the fabrication.
Nice, thank you. I see a question from Laszlo. Nice. Hey, Laszlo, nice to meet you. No?
Hi.
Hi, yeah, here you are. Hi, Laszlo.
Really great work, Marcus. Congratulations. A quick question regarding the photon energy and the size. What is the upper limit? Can you do it for 100 eV, maybe up to kilo electron volts? And size, can you make it a little bit larger, let's say like 2-3 millimeters?
Yeah, so the size is not really a limit, I think. We're using 2 millimeter membranes where 1 millimeter is patterned. And so we can also pattern the whole 2 millimeter. I know that Norcada sells membranes up to 5 millimeters, which are freestanding. So I think this should also be possible. I think larger than 5 millimeters will get challenging without the support, just by the membrane breaking, because it's so thin. For the photon energy, it's the same as I said to Raini now. It's the fab. It's not the fundamental limit, because there are materials all the way up to 120 eV, and then I think I didn't check above 120 eV. But you have to be somewhat wavelength scale with your holes. So whereas this might be possible at 10 nanometers, I think it's impossible like at 2 nanometers, because then what's a hole? It's like 2 missing atoms. That's a problem.
Yes. Thank you very much.
Thank you.
All right. I don't see any other hands raised for questions. Also, nothing in the chat. If there are no other questions, then thank you once again, Marcus, for this nice presentation and the answering our questions. Thank you very much. And we move on to the third talk in the session, given by Nikolai Shvetsov-Shilovsky. Nikolai, I guess you can just share your screen. Okay, I see it's coming up.
Can you see it?
Yeah, we see it.
Okay, in the full mode. Now it's better.
No, it's not in the presentation mode. Now it's in the presentation mode.
It's the presentation mode.
All right. So Nikolai comes from Leibniz University Hanover. He will talk on deep learning for retrieval of the internuclear distance in a molecule with fixed or moving nuclei from photoelectron momentum distributions. Thanks a lot, and I'm looking forward to your talk.
Thank you so much, Rainer, for your very nice introduction. First of all, I would like to thank the organizers for the possibility to present this work here. And as always, it's a big honor and great pleasure for me to present the results from the Laser Physics Conference. So this is the short content, let's put it that way, of my talk. So first of all, I would like to say a few words about photoelectron momentum distributions and time-resolved molecular imaging, and discuss connection of internuclear distance and interference patterns. Then I will say a few words about neural network and deep learning, making some kind of short crash course, and about application of deep learning in strong field physics. And then I plan to come to our results, to our numerical experiments and results, including transfer learning, comparison with alternative approaches, application of visualization methods for this problem, and last but not the least, retrieval of the time-dependent internuclear distance in a molecule in a pump-probe scheme, so for the case of moving nuclei. And then I'll come to the conclusions. It is very well known that photoelectron momentum distributions produced in strong field ionization encode a lot of information I would say, not only static, but also time-resolved information about both photoelectron and the atomic or molecular ion. And there are presently several techniques for time-resolved molecular imaging. For example, laser-induced electron diffraction, which is sketched on this figure taken from the paper by Blaga and authors, or strong field photoelectron holography. So these holographic fringes that are schematically shown here are resulting from interference of direct and rescattered electrons, and they include also a lot of information about the molecular ion. But let us consider a question. What are the imprints of the nuclear motion in electron momentum distributions? To my great surprise, to the best of our knowledge, this problem has not been investigated so far. Even if we consider a simpler problem, if we, for example, we treat nuclei as frozen, and we are interested into the changes of the interference structure with varying of the internuclear distance, what are these changes? To the best of our knowledge, there is only one paper on this issue by Bian and Van Rauch, published in 2014, and the result was that these changes are not very large. Nevertheless, we decided to readdress this question, and also we would like to understand how to retrieve the internuclear distance from the photoelectron momentum distributions. To this end, we solved two-dimensional time-dependent Schrödinger equation for H2 plus molecule with frozen nuclei for different internuclear distances. For quite a moderate laser intensity, standard 800 nanometer pulse with two optical cycles. Here are the results for internuclear distance equal to 2 atomic units, 5 atomic units, and 6 atomic units. It is seen that these patterns and the momentum distributions as a whole, and also interference patterns, change with varying of the internuclear distance. But the question is how to quantify these changes and how to retrieve the internuclear distance from a given photoelectron momentum distribution. We tried several different approaches, and actually, when we failed with them, we turned to application of neural network. To be more specific, to application of deep learning. I don't have a possibility to provide an introduction into this huge topic, or of artificial intelligence, deep learning, neural networks, and so on. But just a few words. So, as you know, neural networks consist of layers of neurons, and every neuron receives the signals from the neurons of preceding layers, has also some bias, and these signals are weighted with some weights, W1, W2, and W3 on this figure, and then using this result, every node calculates actually its output, the so-called activation function, which very often looks like a sigmoid. Deep neural networks consist of more than one layer, and convolutional neural networks are special neural networks that are used to work with images. So look what has happened with this poor dog after it was given to a convolutional neural network. Normally, convolutional neural network consists of pairs of layers, namely convolutional pairs of convolutional layers and average pooling layers. Convolutional layers convolve the image that it receives with certain filters, and average pooling layers average part of the image, and in doing so reduces the size of the image. So our neural network that we have designed for the problem at hand consists of 5 pairs. Of 5 such pairs, of 5 pairs of convolutional layer and average pooling layer. And the last layer, the top layer of the neural network, is fully connected layer that actually predicts the internuclear distance based on a given photoelectron momentum distribution. I would like also to say that actually deep learning becomes a very rapidly application of deep learning becomes a very rapidly developing topic in strong field physics. And this list of papers where people apply neural networks and deep neural networks for strong field problems is of course very far from being complete. I would like only to highlight two papers. The paper by Biggers group, where they used a convolutional neural network for laser-induced electron diffraction, and a paper by Lyutova, Spanner, and Tamblin, where they used neural network in order to predict the high harmonic generation spectra based on only few parameters like molecular orientation, laser intensity, or a wavelength. And so we trained our neural network. To this end, we calculated few thousand, 3,000 photoelectron momentum distributions for different internuclear distances in the H2 plus molecule between 1 and 8 atomic units, and for different intensities between 1 and 4 times 10 to the 14 watt per square centimeter. We split this set into two subsets: training set that was used for training and test set that was used for test. And we trained a neural network to retrieve an internuclear distance from a given electron momentum distribution. We characterize the quality of this retrieval with the mean absolute error. And as you can see from this figure, the neural network does its job with a very good accuracy. The mean absolute error for retrieval of R is less than 0.1 atomic unit. Okay, then the next question appears. Can the CNN, the convolutional neural network, retrieve more than one parameter? And the answer is yes. We trained another neural network to retrieve both the internuclear distance and the laser intensity. As you can see, both parameters can be retrieved with very good accuracies. What's even more interesting, the fact that we are now retrieving two parameters doesn't affect the accuracy of retrieval of R, of the internuclear distance. At this point, you could interrupt me and say that in any real experiment, the laser intensity is fluctuating over the laser focus. And what is actually measured is not this beautiful figure with many interference bulbs, but actually a focal volume average results. So if we take focal volume average momentum distributions and apply our neural network to them, what will be the result? The answer is here. As you can see, the error is larger. It's 0.86 atomic units. Especially bad is the situation here for larger internuclear distances between 6 and 8. What to do? Well, the simplest way out is to train a new neural network which can retrieve the internuclear distance using focal volume average momentum distributions. So we calculated a set of focal volume average momentum distributions and trained a new neural network which allows us to reconstruct the internuclear distance. And here the result is much better. 0. mean absolute error is equal to 0.14 atomic units. But this brings us to the question, what to do in general situation? If we have trained a neural network which solves some problem, and then we would like to apply this neural network for a similar but slightly different problem. Do we have to train a new neural network every time? The answer is not, because we can use the so-called transfer learning technique, which is quite a popular and very widely used technique of artificial intelligence. Suppose we have a neural network that is trained to solve some problem, and then we would like to make a neural network that is able to solve some other problem which is similar to the first one. What should we do for this? We should freeze the weights of almost all layers of our neural network and retrain the rest of layers using a small data set designed for the second problem. So we do here in our case. We freeze 3 first pairs of convolutional layers and average pooling layers, and retrain the last 2 layers, the top layers of our neural network, using the focal volume average momentum distributions. Why does it work? Well, it works because different layers of a neural network learn different features of the image. These layers in the bottom, the first, the third, and the second, and the third one, they learn the very coarse features of photoelectron momentum distributions. And the top layers that we retrain in the transfer learning technique, they learn fine details of our pictures. And we applied the transfer learning technique and made our neural network applicable not only to focal volume average momentum distributions, but also to the distributions obtained for larger internuclear distances, for non-zero orientation angles between the molecule and the laser polarization direction, and also for the case of fluctuating carrier envelope phase. This is a typical example of initial momentum distributions, and this corresponds to focal volume average, to focal volume averaging. This is a larger internuclear distance, 10 atomic units, 10.9 atomic units, non-zero angle between laser polarization direction and molecular axis, and fluctuating phase, 4.50 radians. And in all these four cases, our neural network, after we apply transfer learning technique, is able to solve the problem with quite a good accuracies that are shown here on all these figures. Moreover, by applying the transfer learning technique, we made our neural network applicable to a different molecule. We considered first H2 plus molecule, and now we want to retrieve the internuclear distance in a very asymmetric helium H plus molecule, which is described by completely different potential. And this is the example. Of helium H plus. Sorry for the small defect. As you can see, again, the convolutional neural network makes its job with very high accuracy, the level of 0.13 atomic units. We also compared this approach, I mean retrieval of the internuclear distance with machine learning, with alternative approaches that were used before the neural networks became so popular as they are popular now. What are these approaches? For example, the direct comparison. We can calculate some set of momentum distributions and retrieve internuclear distance just by comparing a given momentum distribution with all the distributions of the set. With this comparison, we can use not only mean squared error in order to compare two figures, but we can use even more sophisticated technique, like, for example, a scale invariant feature transform, SIFT, a technique used in computer vision. Or we can use support vector machines that were very popular in the 90s and beginning of the 2000s, or decision trees. I will not go into all details. In a nutshell, all these approaches can be used for the problem at hand. They all can retrieve the internuclear distance with quite a good accuracy. The problem is that they all have very limited transferability. So as soon as you try to apply them for slightly different conditions, like we did here with transfer learning technique, they will fail. And the only way to make them transferable is just to calculate new momentum distributions and retrain them, which is computationally very demanding. That's why we assume and we think that the convolutional neural network and the artificial intelligence is the proper approach to the problem at hand. Then I would like to say a few words about a so-called problem of visualization of convolutional neural network. Every neural network is by its very nature a black box. We don't know how does it take its decisions. And in principle, it would be very nice to understand this. It would be of course very nice, but in reality, it is very difficult. And even in this field, in the field of artificial intelligence, this problem, which is called problem of visualization of convolutional neural network, is quite difficult. And the first papers, to the best of my knowledge, on this topic appeared about 10 years ago, about 2012 to 2013. Nevertheless, we have taken one of the simplest methods of visualization, so-called occlusion sensitivity technique, and applied it to our neural network. To be honest, most of these methods, they are designed for classifying neural network, and we have regression problem. So we have to retrieve the internuclear distance. And these methods, visualization methods, they work for classifying neural networks. That's why we train another neural network that does classification, that classifies a given momentum distribution with respect to the internuclear distance. And then we applied occlusion sensitivity technique. And in doing so, we were able to extract those parts of photoelectron momentum distributions, they are shown here on these figures as examples, that are used by a neural network in taking these decisions. And in order to be sure that indeed we get something reasonable using visualization methods, we made an independent simple classifier based on the extracted features. And this classifier gives us a prediction accuracy on the level of roughly 70%. So indeed, it is possible to create, if you wish, a dictionary or an atlas of features, which will allow us to even without a neural network to say what was the internuclear distance. And the last point of my talk is the application of this technique to the moving nuclei, to the case where the molecule is dissociated. To this end, we simulated a very well-known pump probe scheme. So the first pulse of moderate intensity excites the molecule to the first excited electronic state, as shown here on this insert, and therefore initiates the nuclear motion. And this nuclear motion we treated classically. So we calculated solving this Newton equation of motion, where this energy is just the Born-Oppenheimer potential surface. In our case, it's just potential curve. And then the second pulse, which acts with a certain time delay, delta t, ionizes the molecule at a certain distance r. That depends on this time delay, and we assume that the internuclear distance corresponds just to the center of the pulse. Then we took our neural network designed for frozen nuclei and applied it in this case, in the case of moving nuclei. And we got that the internuclear distance can be retrieved with the accuracy of 0.26 atomic units for 2-cycle pulse. For 1-cycle pulse, naturally the accuracy is better, 0.21 atomic units, because because the internuclear distance here is better resolved since the pulse is shorter. Of course, these results can be further improved by applying transfer learning technique. This is an ongoing project. We haven't done it. Moreover, since atomic nuclei are not classical particles, they are also quantum particles, we solved time-dependent Schrödinger equation for nuclear wave function and considered photoelectromomentum distributions as an incoherent sum of electromagnetic distributions at different internuclear distances, weighted with the modulo square of this nuclear wave function. And again, we applied our convolutional neural network. And again, we got pretty nice results, 0.26 atomic units for a neural network that is trained for fixed internuclear distances. And this brings me to our conclusions. So we used a convolutional neural network to retrieve the internuclear distance of the 2D H2+ molecule, which was ionized by a strong few-cycle laser pulse using photoelectromomentum distributions. Our neural network that is trained, which was trained only on a few thousand images, and this is not 10,000 or 100,000. Only a few thousand images are enough here. Can predict this unknown internuclear distance with an absolute error less than 0.1 atomic units. Then, the transfer learning technique allows us to make the CNN applicable to momentum distributions obtained at parameters it was not explicitly trained for, whereas alternative approaches that exist in this field show very limited transferability. We have also used the occlusion sensitivity technique in order to extract the features that allow our neural network to take its decisions. And finally, this convolutional neural network trained on distributions for fixed internuclear distances can be applied for retrieval of time-dependent bond lengths. And with this, I would like to thank you for your attention.
Yeah, thank you very much, Nikolai, for this interesting talk. We also made some efforts on training neural networks to retrieve attosecond streaking traces. Also very helpful technique. It's great that you made so much progress. I start with the first question.
Yes.
You said when you have a slightly different problem, then a transfer learning effort is less expensive, so to say, than training the whole network again, right?
Yes. Yes.
Could you kind of quantify this? I mean, is it like just in times of computation or so, right?
Well, look, for example, to train our initial neural network, we needed a few thousand momentum distributions, about 3,000 momentum distributions. If we want, for example, to make our neural network applicable for focal volume average distributions or distributions for larger internuclear distances, for all these cases, we need about 600-700 of momentum distributions. So I would say roughly, if not factor, between factor of 10 and factor of 5, which is of course very large. Honestly, I even did not expect this. But on the average, 700 is the upper limit for transfer learning. So you indeed freeze this all this bottom layer and retrain these two last pairs with a relatively small amount of distributions, and this is enough.
All right, thank you. Yeah, good idea. Great. I see Barry asking a question.
Thank you for a very, very nice talk. I'm interested in hearing a little bit more about your occlusion sensitivity technique. In other words, trying to figure out what the neural network used to make its decision. And yes, exactly this slide. So when you look at this, particularly the regions that it said, this is very important, is there some sort of classical analogy? What did you, like, what am I looking at here? Because especially like at 4.3, 2.5, 10 to the 14, that's two very narrow regions that it's looking at. Do you have any physical interpretation from what it learned?
At the moment, I wouldn't say that we have a clear, honestly, I wouldn't say that we have a clear physical interpretation. But this is an ongoing project, so we are still working on this. In principle, occlusion sensitivity, how it works? It is like a gray square which occludes part of this image, and then it moves along this image. And then at every move of this gray box, neural network tries to classify images again. So in doing so, we are able to understand how important is this occluded square for the classification. If it works good, then this square is not important at all. If it works bad, then it is quite important. I agree with you that it is indeed quite difficult to extract physics from this, to say why is it like this. We are still working on this project. The problem in this field is that there are many methods of visualization. Not only occlusion sensitivity is probably the simplest one, but there is this GradCam, inverted GradCam. There are really many of them, and very often they give some contradictory result. That's why, I mean, everything. We should be really sure that what we get makes some sense. At least, I can state this, since we built an independent classifier based on these features, and this classifier somehow works. I mean, 70%. It's not just coincidence. I randomly took parts of the same square and build some fake classifier. It will give you about 20%. So there is indeed something behind, but future studies are definitely needed to understand this. Probably it's even more illustrative to apply such technique to focal volume average distributions, where we don't have this pronounced variation, where we don't have such a pronounced interference patterns. Hopefully next time I will be able to.
Thank you very much. I appreciate the explanation.
Yeah, thank you. Also from my side, we have another question from Christoph Lemel.
Hi, Nikolai. Thank you for your presentation. I have a question concerning the last part of your presentation about the you averaged over the vibrational wave packets. Yeah, here. I mean, first of all, the true R, what is this R? Meaning, is this the equilibrium position, or what is this? And and the second question is, the larger the R is for whatever molecule, then the width of the wave packet should be larger. So I would expect that the predictive power of your method should be less. But here the error goes up for small r, but goes down for large r. That's somehow not understandable for me, at least.
Christoph, this is also a good question. But as I told you, this is an ongoing project. I mean, this part we are working on it during, I mean, the last, I would say, months. So we don't have all the answers on the questions. Yes, you are right. Of course, I mean, we started from some equilibrium. What we actually did, we consider this direct transition. So we have taken the nuclear wave function that corresponds to this state, and then we solved this time-dependent Schrödinger equation for nuclear wave packet using this energy. Using this energy. So we instantaneously promoted this wave packet, and then it if you wish, it moves along this energy surface. So indeed, it spreads in time. So first, this wave packet, it's a 1D wave packet. It's first narrower, then of course it spreads. Then at every time we have a distribution of our R's, and we calculate photoelectron momentum distributions that correspond to these two different R's, and we weight them with this modulus square of the nuclear wave packet, and then we give the resulting distributions to our neural network. To answer your question, we are still working on this, and I would agree with you. I would also expect better results here for smaller R, where this wave packet is narrower compared to this case when it's actually more spread. Maybe it's because somehow this case, even for these smaller R's, are more difficult even for initial neural network that is trained for fixed internuclear distances. We have also seen this effect. Maybe it's somehow connected, but at the moment, well, we are still working on this. The only thing that I can say.
Thank you.
Sorry, I was muted. All right, thank you very much.
Thank you so much.
Don't see further questions. Also, I don't see anything in the chat. So thank you once again, Nikolai, for the talk and answering the questions. And thank you to all the speakers. Is this a hand rising, Barry, or is it still the old? Wait, you were clapping your hands. Oh, sorry. Yeah, perfect. Thank you. So let's thank all the speakers again for this very nice session, and thanks for staying in time. And I hope I will meet many of you in the afternoon session in about 2.5 hours. All right. See you later. Bye-bye. Thank you.
Yeah, bye.
Thank you. Bye.
Goodbye, everybody.
Thank you.